Welcome back, students. In this lesson, we'll be discussing Chapter 9 in the Klein textbook, which is alkynes. We're going to get started with alkynes by discussing what defines an alkyne, the bond angle of an alkyne, some different examples of an alkyne, and finally, nomenclature of alkynes. So first of all, an alkyne is a molecule that possesses a carbon-carbon triple bond. You can see that demonstrated here. So we have the functional group, which exists between these two carbon atoms. So here's carbon 1 and carbon 2 of the alkyne. And notice that there's a sigma bond between those two carbons bearing the alkyne functional group. And then we have two pi bonds. Those pi bonds exist perpendicular to each other. Now, the blue and red here doesn't denote the two different pi bonds. What that denotes is the positive and negative sign of the wave function. If we want to visualize where these two pi bonds lie, we can outline that. So let's go ahead and take a look at where these pi bonds lie. Okay, so the first pi bond, okay, this is an overlap of the electron density here between the electron in the carbon on the left, so I've outlined that in yellow, and the carbon on the right. So you can see the electron demonstrated here in this orbital as spin up and spin down. So that just means those two electrons are paired in that bond. So that particular pi bond exists in the plane of the paper, or in the plane of the board here. So we have the sigma bond between the two carbons. We have pi bond number 1 outlined in yellow, but a pi bond, an alkyne, a carbon-carbon triple bond, contains 3 bonds, and the third bond then will lie perpendicular to the first pi bond that I have highlighted in yellow. So it's going to extend into the plane of the board and out of the plane of the board. So the second pi bond extends this way, perpendicular to the first pi bond, okay? And when these pi bonds form or break, they form in that way. They form perpendicular to each other. All right, and so notice that this pi bond has a 180 degree bond angle, so that gives it a linear geometry. So a carbon-carbon triple bond is linear, and we have to denote that when we're drawing these, okay? So that means that whatever is attached at the end of the pi bond, in this case we just have the hydrogens, those are going to exist 180 degrees from each other. All right, so if we look at that in an electron density map, we see the regions of high electron density are around the center of the pi bond. Okay? All right, and so alkynes in industry and nature here, we have this natural toxin which is found in the poison dart frog, which contains alkyne functionality. So alkynes are not as common in nature as alkanes and alkenes, but we do find some of them, okay? And so here is a toxin that comes from the poison arrow frog that has this alkyne functionality. So notice that this bond angle on both of these alkynes is demonstrated as 180 degrees. So we have two alkyne functional groups in these molecules, and you can see the bond angle demonstrated as 180 degrees. Okay. An alkyne functional group also exists in this birth control synthetic molecule. Okay, and so we do find alkynes in use. They are found in nature, and they are also found in synthetic pharmaceuticals. In order to name alkynes, we're going to follow the same steps that we used in naming other molecules. Okay, so first we identify the parent chain, and this parent chain in the examples that we have in this book need to include the carbon-carbon triple bond. Okay, so the carbon chain has to include that alkyne functionality in order to name it properly. Okay, so it would only be in rare cases where you would see an alkyne as a substituent, and we aren't going to pursue any examples with that. So then, after identifying the parent chain, we identify and name the substituents. We assign a locant or a number to each of those substituents, giving the carbon-carbon triple bond the lowest number possible. Then we list the numbered substituents before the parent name in alphabetical order, ignoring prefixes except iso, just like we did previously. Alright, and then the carbon-carbon triple bond locant or number is placed just before the parent name or just before the YNE suffix. So we've seen that done with alkenes, and either of those methods is acceptable. Alright, and so just like we did with alkenes, we can use the same method with alkynes with just minor modifications to make it applicable to alkynes. So first we identify the parent chain, which should include the carbon-carbon triple bond. So for example, just like we did pentane before, where we have 5 carbons and just alkane functionality, no alkenes, no unsaturation. All right, we can do the same with pentene. So here we have 1, 2, 3, 4, 5 carbons. We're going to give that double bond the lowest number possible, and therefore this would be 1 pentene. Remember, you can leave the 1 off if the functional group is at carbon number 1, and so this would also be called pentene. If we have a triple bond, notice that this is named similarly, so we have the triple bond at carbon number 1. So we can number this molecule here on the right as 1, 2, 3, 4, 5. So this would be 1 pentyne. So we use the YNE functional group in order to name this molecule. Okay, this would be 1 pentyne because the triple bond is at the first carbon. Okay, so keeping that in mind, we've got to include the carbon-carbon triple bond in the parent chain. So we want the longest chain that includes the carbon-carbon triple bond. So for example, in these two examples here that we have, we see the parent is octane on the left, where the longest carbon chain would simply be the longest chain, continuous chain that we can draw or follow. But on the right, where we have that triple bond functionality, where we have an alkyne functional group, we have to include the alkyne functional group in the parent chain. Okay, and so even if that chain is shorter, even if it's not the longest chain, longest continuous carbon chain available in the molecule, we need to include that triple bond functional group in order to name the molecule properly. And so we have to include that as part of our parent. So the longest continuous chain in this molecule on the right would include 1, 2, 3, 4, 5, 6, 7 carbons. So instead of oct, as we have on the right, where this is our longest parent chain, on the left we would only be able to find a continuous chain containing that alkyne functional group with 7 carbons. Okay, because if we followed this next possibility, 1, 2, 3, 4, 5, 6, we would only have 6 carbons. So the longest one is the one outlined in red, and that is the heptyne functional group. Okay, or I'm sorry, the heptyne would be our parent chain there. All right, and so again, we want to give that the lowest number possible. We want to give our alkyne functional group the lowest number possible. And so, for example, if we could number the molecule, let's say from left to right here, we can give our alkyne the number 2, 1, 2, 3, 4, 5, 6, 7. But on the right, if we numbered from right to left, our longest chain, 1, 2, 3, 4, 5, 6, 7, then our alkyne would get number 5. So remember, the alkyne gets the carbon number where we encounter it first. Okay, so we don't say 5 comma 6, or we don't say 2 comma 3 for the alkyne. We just give it the number of the first carbon where it's encountered in the molecule. Okay, so this would be the parent would be hept. All right, and so we could call this parent here hept 2 ine or 2 heptine. Either one of those would be acceptable. Okay, so we could go ahead and name this molecule. It's not that different. It's not that much of a stretch to go ahead and do that as an example here. Okay, so what would this be? This would be a derivative of 2 heptine. Okay, I haven't written that very clearly. So this would be a derivative of 2 heptine, and I'm talking about this molecule on the left. And what are our substituents? We have 3 substituents, 1, 2, 3, and they're all methyl. So we would have a tri-methyl. Okay, and so we just need to give the locants to those methyl groups. So 2 of the methyls are at carbon number 5, and 1 of the methyls is at carbon number 6. So this would be 5, 5, 6 trimethyl 2-heptine. Okay, now some students may get confused because they may say, hey, well, there's 2 methyl groups on carbon number 6. There's one here and there's one here. But the second methyl is part of the parent chain. So if I highlight that parent chain, okay, I don't count any of those methyl groups or any of those carbons as a substituent. Everything on the parent chain is included in the naming convention as part of the parent. So I don't need to include any of that as part of the substituents. Okay. All right, and so we see how to assemble this name just as we did previously. So we listed the numbered substituents before the parent in alphabetical order, and we placed the carbon-carbon triple bond locant either before the parent or before the suffix yne. All right, so let's get some practice with providing systematic names for the following molecules. Okay, for the first molecule, molecule A, let's go ahead and name this one. So I'm going to redraw it over here. Notice when I'm drawing these molecules, the bond angle between the 2 carbons that are attached, the 2 atoms that are attached to the alkyne, is 180 degrees. So I want to keep that consistent when I'm drawing my molecules. Okay, just pointing that out. So let's go ahead and number these atoms in the parent. So we don't have any substituents here. This is a relatively simple molecule. Okay, so let's number them. 1, 2, 3, 4, 5, 6. So I would number them this way along the red path. Let's try a different path. Let's go from we just did from left to right, so let's go from right to left. 1, 2, 3, 4, 5, 6. Okay, so we have the same numbers for our alkyne functional group, whether we number from left to right or right to left. Either way, our first atom, the first carbon where we encounter the alkyne functional group, would be carbon number 3. Okay, so this is going to be a derivative of what? We have 6 carbons. Okay, no matter which way we number it. So this would be a derivative of hex. Okay, and our alkyne functional group is at carbon number 3, so we could say hex 3-ine or 3-hexyne. Either way works. When you get into more complicated names, the top method becomes a little clearer. So a lot of chemists like to stick with that method, and in fact I like to stick with that method as well. Alright, so that's the first one. When we get to the second one, okay, we're going to encounter a substituent. Okay, so remember, we want to give our functional group or our alkyne functionality the lowest number possible first, and then second we want to give our substituents the lowest numbers possible. Okay, so let's number this either from left to right and then from right to left. So we're doing B here. Let's go ahead and redraw the molecule. Okay, so let's number it from left to right. 1, 2, 3, 4, 5, 6. Okay, now let's number it from right to left. 1, 2, 3, 4, 5, 6. Okay, now you might say, well, why didn't I number this methyl down here as part of the parent? Well, it doesn't matter. Either way I do it, I'm going to have the same name. 1, 2, 3, 4, 5, 6, for example. Okay, so my alkyne functional group has carbon number 3 no matter which way I number the molecule. Okay, so it doesn't matter if I number from left to right or right to left as far as the alkyne is concerned, but if I number from left to right along the green path, I can give my functional group, which in this case is a methyl group, carbon number 2. So I'm going to choose the green path in order to give my alkyne the lowest number, and that's the first priority. That trumps the substituents, but then second to give my substituents the lowest number. Okay, so what's my parent here? My parent is hex because I have 6 carbons. Okay, and my alkyne functional group, numbering from left to right, is carbon number 3. So this would be hex 3-ine or 3-hexyne. Okay, and I just have one methyl group, and that methyl group is at carbon number 2 along the green path. That's the path we've chosen. Alright, so this would be 2-methyl hex 3-ine or 2-methyl 3-hexyne. Okay, so we put hyphens between the numbers and the words, or the numbers and letters. Okay, and then we just assemble the substituents alphabetically. So that was B. Next we'll do example C. Okay, that's this example here. Let's go ahead and redraw the molecule. Notice when I'm drawing the molecule, I'm keeping the bond angle between the atoms next to the alkyne functionality at 180 degrees from each other. Okay, so it's important to draw your molecules properly. So let's go ahead and name this molecule. So 1, 2, 3, 4, 5, 6, 7, 8. So this is a derivative of oct. The parent would be oct, and my alkyne functionality starts at carbon number 3, so this would be oct 3-ine, okay, or 3-octyne. Now we don't have any substituents here, so we can we're done. Okay, so let's go ahead and do D. So D. Okay, so let's rewrite D. Let's rewrite D. Let's turn it around. I'd rather have it this way. Now what is over here? Okay, so notice that, remember that carbon forms 4 bonds, so if I draw this molecule out, on the end I have a CH, then I have a double bond to another carbon, then a double bond to this carbon that has 3 methyl groups. Just drawing everything out, okay, just making sure you can recognize that. Alright, so let's go ahead and number this. We want to give our alkyne carbon the lowest number possible, so this would be 1, 2, 3, and what's our longest carbon chain? 4, okay? our longest carbon chain is 4. Now we're going to look at another way to name this molecule in just a little bit, but for now we're sticking with the IUPAC standard way, and that would be to include the longest chain in our parent. Okay, so this would be a derivative of butane. Okay, but we have the triple bond, so this would be butine. Now we could say 1-butine because our carbon triple bond starts at, our carbon-carbon triple bond starts at carbon number 1, right? So we could say but1-ine or 1-butine, but since it's at carbon 1, we can just leave it off, okay? Because it's understood to be at carbon 1 if we leave it off. And then notice at carbon 3, we have 2 substituents, and both of those substituents are methyls. So we have to put that 3 twice to indicate that both methyls are at carbon 3. You can't just say 3-dimethyl because that's incorrect. So it's 3, 3-dimethyl, okay, butine. Okay, so if you said 3-methylbutine, it would be as though one of those methyls was a hydrogen. And if you just said 3-dimethylbutine, that's a little bit confusing because someone may assume that you had a methyl somewhere else. Actually, for this molecule, I don't think you could put the methyl anywhere else, but we still have to put the 3 twice, okay? All right, so this is 3,3-dimethylbutine. Okay, for the last example, E, we get a little bit more complicated. So let's go ahead and do the last example on this page. All right, so let's number and see what our longest carbon chain is. 1, oh shoot. All right, so 1, 2, 3, 4, 5. Now we could go either up or down at this point, and I'm going to go up first. 6, 7, 8, 9. So along the red path I have 9 carbons. What about if I had went along the lower path? 1, 2, 3, 4, 5, 6, 7, 8. So along the lower path, along the green path, I have 8 carbons. So my parent is non. 9 carbons is non. And my alkyne starts at carbon number 1, so that would be nonine. So I can leave the 1 off because it's understood to be number 1. Now let's circle our substituents. I have 1 here, and what is that? That is a 1, 2, 3. That's a propyl group. Okay. And then remember, we're going along the red path, so let's highlight the red path. All right, now I have a substituent here, which is a methyl. So actually this isn't a very complicated example, it just looks complicated at the beginning. So at carbon number 5 I have a propyl group, and at carbon number 7 I have a methyl group. So methyl comes before propyl, so that's 7-methyl, 5-propyl. So even though 5 comes before 7, I'm going to put the methyl first, so that would be 7-methyl, 5-propyl, nonine. Okay, so that is the name for example E. Moving on, we have a few more problems with translating structures to names, and then we have a couple of problems translating a name to a structure. Here I've drawn a guide, which is the parts of a name of an organic molecule. So I'd like to demonstrate how to use this guide in naming. Notice the parent here is the central part of our guide, okay? And on either side we have different other parts of the name. So the first thing we do is identify the parent, and then we can add these other features in if they exist, and this guide helps us to assemble the name. So we have the parent in the center, then we have unsaturation if it exists, so that would be like an alkene or an alkyne, and we have functional group at the end. Now we don't have another functional group here, so we would just end with the ending YNE for our alkyne. And for substituents, we're going to again assemble those alphabetically with their locants, okay? And then we have stereochemistry way out in front if it exists. Now in this case, we don't have stereochemistry, so that would be like cis and trans, R and S, okay? So that goes out in front. So in order to begin nomenclature for this molecule, what we're going to do is identify the parent, which contains the highest priority functional group, which in this case is the alkyne. So let's go ahead and number this parent. 1, 2, 3, 4, 5, 6, 7, 8, 9. Now if we'd gone this way, we would have had 6, 7, so that would have been shorter. So the path that we've chosen is the longest path, okay? So our parent is non, okay? So the parent is non for 9 carbons, right? Now we don't have a functional group other than the alkyne, so we're going to enter YNE for the unsaturation. Okay, we need to put our locant there. In this case, the first carbon of the alkyne that we encounter is carbon number 3, so this would be 3-ine, or you could say 3-non-ine. And then we just have substituents because we don't have any stereochemistry. So what are our substituents? I'm going to get a different color here. Okay, we have this one, which is ethyl. Okay. All right, and the ethyl is at the 5th carbon, so we could call that 5-ethyl. And then we have 2 methyls here, so that would be 6,6-dimethyl. Okay. All right, so we don't consider di in our naming, but we have M versus E. So the E comes first, not because 5 is before 6, but because alphabetically E comes before M. So we would assemble this name in this way. This would be 5-ethyl, 6,6-dimethyl, non-3-ine. Okay, so in this way our guide can help us assemble the name of our molecule. Now let's go ahead and do the next one. I'll go ahead and erase this. Now I had this white here because I was drawing my molecule up into that area. Alright, so let's go ahead and erase everything and we'll get started with the next one. So the next one, maybe I'll just try to use the molecule as it is drawn. Well, let me go ahead and redraw it. It's pretty small. So we have Cl3. Let's go ahead and draw those out. Okay, I have a carbon with 3 chlorines right here, and then I have a carbon of the alkyne, and then another carbon of the alkyne, and then a carbon with 2 methyls. Then we have an alkyl chain. Alright, so let's identify our longest carbon chain containing the alkyne. So our carbon number 1 is going to be right here, not here. The chlorine doesn't count in that parent chain. So this would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the longest carbon chain is 10 carbons, so the parent is dec. And we have an alkyne, so we're going to end that with YNE. We don't have any other functional group, so we'll end with YNE. And that alkyne functional group begins at carbon number 2. So that's dec 2-ine, okay? Now we need to identify our substituents. So we have 1, 2, 3 chlorines. We have 2 methyls, and then we have an ethyl. Okay. So the 3 chlorines that are at carbon number 1, so that would be 1, 1, 1. You have to put the 1 3 times. Trichloro, okay, and then we have 4, 4 dimethyl, right, and then we have 8-ethyl. Alright, and so alphabetizing these, we don't count the T for tri. This would be C for chloro, versus M for methyl versus E for ethyl. So that would be chloro, ethyl, then methyl. Okay, I'm not sure if we can get this all on this line, so I'll start writing below. Okay, so beginning with chloro, that would be 1, 1, 1. Trichloro, 8 ethyl, 4, 4 dimethyl, and then just finally adding the parent and unsaturation, dec 2 ine. Okay, so that's how we would name this molecule. For the next couple of problems, we'll be translating a name to a structure. So for 9.2a, we have 4, 4 dimethyl 2-pentyne. So we'll begin with the parent, which is pent. Okay, how many carbons is pent? That's 5. Okay, so let's draw a 5-carbon chain. Now this is a 5-carbon chain, but remember that we have an alkyne functionality at carbon number 2. That's why we have 2-pentyne. So let's begin instead by drawing our alkyne functionality, and then we're going to put that at carbon number 2. So alkynes are a little trickier than what you may be accustomed to drawing, because if you just use your regular method of drawing an alkane, it won't come out correct. You need to make sure that your bond angles are linear, representing the alkyne. So I like to begin by drawing the alkyne and then assemble the alkyne functional group and then assemble the rest of the molecule around it. So notice that I've drawn the alkyne functional group at carbon number 2, okay, and then at carbon number 3 is the second carbon in that functional group, okay, and so we have pentyne, so that'd be 1, 2, 3, 4. So that's also linear, and then we can begin to bend when we add the next carbon. So this would be 4, 5, okay? And the rest of the molecule is 4, 4 dimethyl, meaning we have 2 methyls at carbon 4. So that is the way we would draw this molecule. For our next example, we'll do problem B of problem set 9.2, 5-ethyl, 2,5-dimethyl, 3-heptyne. Our parent in this case is hept, okay? So we have heptyne, which is 7 carbons, and the alkyne functional group is at carbon number 3. So I'll begin drawing the alkyne functional group, and that means this first carbon is going to be carbon number 3 if I'm drawing it from right to left, okay? And so the next carbon over also has to be linear, and then we add another carbon to complete that end of the chain. So this would be 1, 2, 3. Okay, and we need 7 carbons total, 4, which is also going to continue to be linear, and then we can bend the chain 5, 6, 7. Okay, so 4, 5, 6. Oh, I got too many carbons. Okay, so 1, 2, 3, 4, 5, 6, 7. So that's 3-heptyne. Okay, so let's go ahead and erase the numbers. Well, maybe I'll leave them. I'll leave them on the top. Okay, so now we have 5-ethyl, 2,5-dimethyl. So at carbon 5, we have an ethyl group. Okay, so it's going to be 1, 2 carbons coming off of carbon 5. And then 2, 5 dimethyl. So that means 5 also has a methyl and 2 has a methyl. Okay, so we actually have, let me clean that one up a little bit, 2 methyl groups. Alright, so that looks a little better. So that would be the way we would draw 5-ethyl, 2,5-dimethyl, 3-heptyne. For this next problem, we'll work problem 9.3. When naming cycloalkynes, the triple bond does not require a locant because it's assumed to be between carbons 1 and carbon 2. Draw the structure of R 3-methyl cyclononine. Okay, so let's begin, as we did previously, by drawing the alkyne functional group, and then we have to continue to make the carbons on either side in a linear fashion. So that gives us 1, 2, 3, 4 carbons, right? So now we still need to add 5 carbons. So this would be 2 more. So that'd be 1, 2, 3, 4, 5, 6. And now we need to add 3 more to get 9. So 1, 2, 3. Okay, so that's 9 carbons. So let's number these to make sure. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, now at carbon number 3 we have a methyl group, and we need to give that methyl group stereochemistry. So this is our methyl cyclononine. So let's just choose to make the methyl group coming out at us. Let's put it on a wedge, and let's see if that's R or S. Okay, I'm going to go ahead and change colors, and let's draw in our hydrogen. That would be by default on a dash. So the hydrogen would be number 4. The carbon with the methyl has 3 hydrogens on it. That'd be substituent number 3. If we move, so we're looking at this carbon here and we're giving it stereochemistry. Okay, that carbon there. Okay, so the hydrogen's number 4. This methyl group, that carbon has hydrogen, hydrogen, hydrogen. So it's going to be the second lower priority, so it's number 3. And now we're comparing the carbon at carbon 4 versus the carbon at carbon 2. Carbon 4 has a carbon going this way, so we're moving away until we find the first point of difference. So it has a carbon, which is carbon number 5, so carbon, and then it also has 2 hydrogens. So carbon, hydrogen, hydrogen, and carbon 2 has carbon, carbon, carbon. So carbon 2 is going to be priority number 1. Carbon 4 is going to be priority number 2, and then we've prioritized the other 2 already, the other 2 substituents already. All right, clean up some of this. Okay. All right, so we've got, so this carbon is carbon number 2, this is carbon number 1, number 3 is coming out at us, and the hydrogen is going back. So this is 1 to 2 to 3. The progression of rotation is R. So in fact, this is our 3-methyl cyclononine. We can also name alkynes using common names where the alkyne functionality is in the center, and we name the things on either side. So this would be as though our parent is acetylene and we're naming the groups on either side of acetylene. Okay, so acetylene is a carbon double bond with a hydrogen on either end, because we can only attach one other thing. So acetylene is the simplest alkyne, and we could name molecules in that way. This is a common way of naming them. It's still accepted in the IUPAC nomenclature, but this is considered a common name. So if we have an alkyne functional group and a methyl on one side, this would be methyl acetylene. In this case, we have an alkyne with an isopropyl on either side, so this would be diisopropyl acetylene. And in the next case, we have a benzene ring on one side. A benzene ring is called a phenyl group, and we have a propyl on the other side, so this would be phenyl propyl acetylene. We'll look at a couple of examples in just a minute. And I want to also point out that alkynes can be what's called terminal or internal. And we're going to see that that makes a difference chemically. They react differently whether they're terminal or internal. Okay? A terminal alkyne has a hydrogen, and an internal alkyne does not. Okay? An internal alkyne is wedged between carbons, and a terminal alkyne has carbons on one side but a hydrogen on the other. Okay? So let's go ahead and work a couple of problems naming these using the common name method. So for A, we have our alkyne functionality, and then we have 2 carbons on either side. So we have 2 carbons on either side of the alkyne. So those two carbons are ethyl groups. So this would be diethyl acetylene. For the next one, we have an ethyl and an isopropyl. Okay, so we again alphabetize them, and remember iso counts for alphabetization, so this would be ethyl isopropyl acetylene. Okay, so for the next one, we have an ethyl group and a 1, 2, 3, 4 butyl group, so this would be butyl ethyl acetylene. Okay, so because we alphabetize them. Okay, so this would be butyl ethyl acetylene.